Okay, so what you're going to go do now in the lab is sort of load in, as I said earlier, the GPy software, and build a covariance using GPy. So in GPy, the covariance functions are in this, because they are sort of also kernels, they're in this sub area called kern. So gpy.kern.rbf gives us the exponentiated quadratic covariance. And when you call it, you can see that you're asking to provide an input dimension. Most covariance functions require an input dimension, and then specify a couple of the parameters. So the two parameters in the exponentiated quadratic are the variance and the length scale. So we're setting a variance and a length scale. So the nice thing is you can sort of then print the covariance function, and it just gives you a table giving you those values. So you can also plot it, and we've got this command kplot, and what kplot does is it gives you what the shape of this covariance looks like, in case you're just interested to see how these correlations decay over space. And you can set parameters of the covariance. So here we're constructing an exponentiated quadratic, and then we're building an array of different thetas, and then we're going through setting the length scale of the exponentiated quadratic to those different values of theta, and then plotting each one. So this is the exponentiated quadratic with changing length scales, yeah? With a nice little legend. So all little sort of helper functions for doing that. So then there's little exercises for you to think about. And there's other covariance functions as well. So this is the covariance function, Brownian, associated with Brownian motion. So because the covariance function associated with Brownian motion is not a stationary covariance, what you end up plotting is the output of the covariance given one input to the covariance. So that's what this showing here. So you don't get this symmetric output because it's non-stationary. Then computing the covariance function in given input data. So here's the return 5 over 2, and you can compute the eigenvalues of that return 5 over 2. And there's a couple of questions for you to think about different covariance functions. So where are we here? Pi combined. So adding covariance functions. So it's easy to just add two covariance functions in GPy. So you just set one covariance to be one type, and then set the other to be the other type, and we've overloaded the operator to give the new type. So here we've got an exponentiated quadratic being added to a Matern covariance, and here's the two just being added. The added covariance contains the parameters for both, and you can plot the result, which is neither a Matern or an exponentiated quadratic on its own. Multiplying covariance functions. So again, we've overloaded the operator to multiply. It's actually renamed the result of the covariance function as an RBF times a Matern 5 over 2, and it has all these parameters here. So you can then sample from the GP in the same way you've been doing sort of manually, by building a covariance and computing the covariance. So the covariance function itself has this method k, which actually computes that covariance here. So that's what we're doing here, and then we're sampling from that covariance with a mean given by 0 and a covariance given by c. So this is just the sort of GPy way of doing what you've been doing sort of manually before. So you know, and I can now do things like I can immediately say plus gpy.kern.matern 5, let's say Matern 3 over 2, and then input dim equals 1, length scale equals, let's say, I don't know, 0.01. I don't know if that's going to give an interesting result or not. So putting that in, yeah, it gives me that I've got this Matern thing going on top of that function now. So I can change, you know, by adding these two covariances together, or I could just put in So that was 0.01, or I could reduce that. And now you've got this combination. That sort of more wiggly behavior is coming from the Matern 3/2. Or we could add linear. I think I can't remember if it's linear or lin. So I need to get rid of the length scale parameter because the linear has no length scale. Is it linear? Yes, linear. And now there's actually linear trends associated with these guys here as well. So it's a linear plus an exponentiated quadratic. So it's designed to allow you to focus on the model. You can show a matrix of the covariance function, obviously. So this one, because it's linear plus RBF, has this sort of weird behavior like that. There's a little exercise there which apparently isn't loading because it's supposed to show you some different covariance functions that you fit to. So next thing is to look at a little bit of data. So there's a data set there, and fit the data using gpy. So in gpy, you build a model. So you build the covariance function, and then you pass that to a Gaussian process model. In this case, the Gaussian process model is for doing regression. And you just pass in the input data, the target data, and the covariance function you want to use. Model plus data equals prediction. So once you've done that, you can just ask simple things like, okay, we can print what the model is. It will tell you the likelihood of the model and the parameters of the model. And you can plot the model. If you plot the model, it will give you the current state of predictions for the model. So it's got a length scale that's way too large and a variance that's quite big as well. Now, we set the parameters. All these parameters need to be constrained positive. Actually, I don't think you need to do this anymore in the current version of gpy. But gpy allows you to put parameter constraints on, like to constrain some things to be positive or to constrain other parameters to be equal to each other, the sort of thing that is quite mechanical to do but a bit tedious to do on your own. So once you've done that, you just optimize the model saying m.optimize, and then we're plotting the result. And now, because that was a noiseless function, we get the updated fit with the updated parameters. So it's got the noise variance down to 0 and the length scale at 0.15. Okay, and finally, we've got our running example. So we're loading in the data from the Olympic marathon again, plotting the data. And in this case, building a fit that says this is modeled by an RBF, an exponentiated quadratic, plus a bias, an overall bias on the covariance function, and then adding the two together, and that's the fit it gives. So you can now play. What I suggest you do is try and get through down to that section, because a lot of the earlier stuff you've kind of done variants of, it's there for you for completeness. But once you get down to here, you can really start playing with this bit here. So for example, here we could set length scale equals 80. This is what I was just saying earlier. And then we could add a gpy.kern.rbf 1 length scale equals 10. So this says now that people improve on an 80-year time scale simultaneously with things go on a 10-year time scale. I want the 10-year time scale to capture things like war, and people stopping doing marathons because of war, and the 80-year time scale is the sort of broad, general, slow improvement I expect. So once I put that in, I can fit that combined model, and now I get this combination of effects. Look, there's the long-term thing, and then here's a slowing up. Look at that. The outlier is pulling the function up too much there, yeah? So this is why the noise model's wrong. We need a non-Gaussian noise model in this case. But we get this sort of little bit of a tweak because it thinks that maybe we got slower in 1904 because of this bizarre little outlier. So, but the long-term trend is going down, but then I get these minor little flicks by adding in that second length scale. Or I could say, well, maybe I don't think it was RBF. Maybe I think it was a Matern 5.2. Yeah? So it looks the same. Can't tell much about the derivative, and the noise is quite large as well. And you can compare all of those models by looking at model.log likelihood. So you can see which one. You have to be a bit careful because sometimes you're adding in additional parameters or taking parameters away, but you can then look at the model.log likelihood to see how well you're doing. So there's all sorts of different questions. I think the value of this is to go down to the end of exercise 5. You are not going to have time to do that in the next 20 minutes. So, but I'd suggest you just start playing with gpi. Maybe run a few of those examples. You're familiar with a lot of stuff. You could probably just sort of head down towards exercise 5a and start playing with this. This is the full setup. Build the covariance function that we specify, put it into a regression model, optimize the model, plot the result, give us the model log likelihood. Okay? So I suggest you head down there. Of course, you need to load in the data. So come down to this sort of point here in the file, and then load in the data, set the data, and then build Gaussian processes. You could even multiply covariance functions together. You've seen that that's possible. So look, we could do this thing here. Instead of adding those things, we can do that. Don't know whether it's sensible or not. We get a different result. And of course, if you want to see what the model's done, you can just add a print model on the end there. Yeah? Okay? Off you go. Questions, I should say, actually? Right, good. Off you go.